Here is an expression with a terrifying tower of powers. Our mission is to prove that for any integer n greater than or equal to 3, this entire quantity is divisible by 1989. Stated in the language of modular arithmetic, we need to show this congruence holds. At first glance, this seems impossible. The numbers involved are astronomical, but number theory provides the tools to solve it elegantly. The key to taming a large modulus like 1989 is to break it down into its prime factors. This allows us to tackle the problem in smaller, more manageable pieces. Let's factorize 1989. The sum of its digits, 1 plus 9 plus 8 plus 9, is 27, which is divisible by 9. So 1989 is divisible by 9. Dividing by 9 gives us 221. Now, what about 221? It's not divisible by small primes like 2, 3, 5, or 7. Let's try 13. 221 is 13 times 17. So the prime factorization is 3 squared times 13 times 17. Because these factors are pairwise coprime, if the expression is divisible by each of them, it must be divisible by their product. This is a direct application of the Chinese Remainder Theorem. Let's begin with the proof of divisibility by 9. We'll split this into two cases based on whether n is a multiple of 3. First, consider the case where n is a multiple of 3. Using p-adic valuation, the number of factors of 3 in n to the n is the exponent n to the n times the factors of 3 in n. Since n is at least 3 and is a multiple of 3, this value is at least 27. Both terms in our expression are therefore divisible by 9, making their difference also divisible by 9. Now for the second case where n is not a multiple of 3. Here, n is coprime to 9. We use Euler's theorem, which states that if a and m are coprime, then a to the power of phi of m is congruent to 1 modulo m. Since phi of 9 equals 6, any number coprime to 9 raised to the 6th power is congruent to 1 modulo 9. This gives us a reduction lemma. To compare powers of n modulo 9, we only need to compare their exponents modulo 6. Our new goal is to show that the difference of the exponents into the n to the n minus n to the n is a multiple of 6. For divisibility by 2, we just need to check parity. If n is even, both terms are even. If n is odd, both terms are odd. In either scenario, their difference is even. For divisibility by 3, since n is coprime to 3, we know that n squared is congruent to 1 modulo 3. This means we can reduce any exponent modulo 2 when working modulo 3. Since n to the n and n have the same parity, the exponent reduction gives us the desired congruence modulo 3. Since the difference of exponents is divisible by both 2 and 3, it is divisible by 6. Let's represent this difference as 6 times k for some integer k. Substituting this back into our original expression gives us this form. We can factor out n to the n to the n. By Euler's theorem, since n is coprime to 9, n to the power of 6k is congruent to 1 to the k, which is 1 modulo 9. This means the term in the parenthesis is 0 modulo 9, making the entire expression divisible by 9. This completes our first proof. Next, we prove divisibility by 13. The logic is very similar, but the modulus is different. The case where n is a multiple of 13 is trivial. Since n is at least 3, both terms are divisible by 13, so their difference is as well. If n is not a multiple of 13, we turn to Fermat's little theorem. We use Fermat's little theorem in its multiplicative form. For a prime p and a coprime to p, we have a to the p minus 1 congruent to 1 modulo p. For the prime 13, this means n to the 12th power is congruent to 1, so we can reduce exponents modulo 12. So our task reduces to showing that the difference of exponents is a multiple of 12. We need to show divisibility by 3 and 4. We have already proven divisibility by 3. Now let's check for divisibility by 4. If n is even, since n is at least 3, n must be at least 4. Any power of n greater than or equal to 2 will be 0 modulo 4. Both exponents n to the n and n to the n to the n are much larger than 2, so both terms are 0 modulo 4. If n is odd, then n squared is congruent to 1 modulo 4. This allows us to reduce exponents modulo 2 when working modulo 4. Since n to the n and n have the same parity, the exponent reduction gives us the desired congruence, modulo 4. The difference of exponents is divisible by 3 and 4, hence by 12. This implies, by Forma's little theorem, that the original two terms are congruent modulo 13, and their difference is 0. Part 2 is complete. Finally, we prove divisibility by 17, following the same beautiful recursive pattern. Again, if n is a multiple of 17, the result is immediate. If n is coprime to 17, we look at the exponents modulo 16. Our goal is to show the difference of the exponents is a multiple of 16. If n is even, n is at least 4. Any power of n greater than or equal to 4 is divisible by 16. Both of our exponents are vastly larger than 4, so the difference is 0 modulo 16. If n is odd, this is where the recursive structure becomes clear. We need to compare the exponents n to the n to the n and n to the n modulo phi of 16, which is 8. To use this reduction, we must first rigorously prove that n to the n is congruent to n modulo 4 for any odd n. Here's the proof. Any odd number squared is 1 modulo 4. Since n is odd, we can rewrite n to the n as n times n squared to the power of the quantity n minus 1 over 2. This simplifies directly to just n modulo 4. The chain of reductions works as follows. Since n to the n is congruent to n modulo 4, we get n to the n to the n congruent to n to the n modulo 8, which gives us the final congruence modulo 16. Thus, the original expression is divisible by 17. We have reached the final step. Let's assemble our results. We have successfully shown that our expression is divisible by 9, 13, and 17. Since these three numbers are pairwise coprime by the Chinese Remainder Theorem, the expression must also be divisible by their product. And that product is exactly 1989. And so, we have proven that this colossal expression is always divisible by 1989 for any integer n greater than or equal to 3. Let me present a compact, fully rigorous version of this proof that addresses all the precision issues we've discussed. Here is our theorem statement. The proof strategy: factor 1989 and use the Chinese Remainder Theorem. For modulo 9, if 3 divides n, use valuation to show both terms are divisible by 9. If n is coprime to 9, reduce exponents modulo 6 using Euler's theorem. For modulo 13 and 17, the same pattern applies with their respective totient values. The key insight is the recursive nature of exponent reduction, leveraging the fact that squares of odd numbers are congruent to 1 modulo small powers of 2. For those familiar with advanced number theory, this entire recursive structure can be unified by the Carmichael function. The value for 1989 is 48. Meaning all coprime cases reduce to showing the exponents are congruent modulo 48. As a concrete example for en equals 3, the divisibility by 9 is handled by our first case, since 3 is a multiple of 3. The divisibility by 13 and 17 is handled by our second case, using exponent reduction. This confirms the logic holds for all parts of the proof. If you found this journey through number theory as fascinating as I did, please consider liking the video and subscribing to the channel for more proofs like this one. Thank you for watching, and stay curious.